Okay, let's get started. So, still about half attendance. I expect more people to show up on Friday. Um, so, just actually quite a few things. So, homework 4 is, of course, due Friday. So, any questions on homework 4? It should be pretty straightforward.
Yeah, so knowing the distribution of like ends that we plot and we're just like plotting like different like random like runs or like just like
Yeah. So so there are a lot of things that you could do here. Um, if you were going to do a table, what you can do is like for a particular choice of like say t is equal to 2, k is equal to 10, b is equal to 2, just random choices. So you can have like a run 1 column, and then a run 2 column, and then a run 3 column, or something like that. And then like the values of n that you get are like maybe 22, 20, 25, 23, something like that. So you can actually just spit out all of the results in a table like this. Or what you could do is to have a plot where you have like say same situation, but you have like say run 1 down here, and then what you plot is a bar graph right here, which is say the average of the ends that you produce in run 1. So if the average over here is 23.2, for example, then here at 23.2 you plot the first run. And then the second run, that might be a different one. The third one would be maybe this one. So you just plot all of the results in some way that would make sense. So there's no specific way of doing it, but as long as you can show the results of the values of n that you get, that's fine. Yeah.
so like how do you know like different like n values of one run one? Like isn't like run one n value of run two?
So each run is okay, I see what you mean. By run 1, I mean the doing the same method multiple times. But you're right. You could interpret that to mean we have like say 100 runs in total, and then each one of those is a specific n value. Yeah. So what you could do is to say have run 1 here, run 2 here, etc., up to say run 100, maybe in sorted order. That might be a good way to visualize it. Yeah, so you could just say each of these runs that have a bunch of ends is for a specific choice of TKV. That's another way that you can interpret it. Yeah, so this question's pretty open. So it's not like there's a specific way that you have to do it, as long as you can show some adequate knowledge of how to implement the algorithm and getting a bunch of different results because it's a random algorithm. That's fine. Yeah.
You have to generate that table by using the program, or you can use it manually.
Oh yeah. The table and the plot you can do manually. Yeah. Yeah. So it's not. Well, obviously the program has to be implemented, but the table you can create it however you like in Excel or LaTeX if you know how to do that. Yeah. Other questions about homework 4? Okay. So in the problem-solving session today, what I'll do is if you have any questions about the project, like I'm not sure if I want to do this one, or I'm not sure what this one's asking, but it sounds interesting, or I have no idea whatsoever which project to do, then feel free to come in and ask me questions and we can talk through it about what would make sense. So are there any questions about the project itself? So remember, what's due in a few weeks? The proposal. So you have to know who you're going to be working with, as well as what day you want to present. So in the doc down here, I have 6 days. Only one person has actually told me what day that they want to present. So they come on a first come, first served basis. So make sure to pick the one that you want, and then I'll assign you if it's available. Okay, any questions about the project though, otherwise? Okay, I just posted, and I probably should have done it earlier, sorry about that, the density code. So remember we were talking about that conditional expectation algorithm that's deterministic. So it's a deterministic version of the algorithm you're implementing in homework 4. So we went over this before, and I just want to show you that it actually does produce a covering array at the end. So if I put the strength to be 2, 5 columns, 2 symbols, and redundancy 2, so lambda equals 2, then I get, I think, 8 rows out of here. And it turns out that that's optimal. So if I wanted to change this to 20 columns, it takes a little longer. It gives me an initial estimate on the number of rows. And as I'm producing rows, the estimate gets better and better and better. Yeah, so there are some people who told me that they wanted to work on something like this. So there's a lot that you can do here. So I posted the code on Slack so you can play around with it. Okay, so I think that's all I need to say about that. So let's get back into, I guess, to new material, because we finished anti-random and IPO before. So what are all the algorithms that we talked about? So we talked about exact algorithms first, and then we talked about greedy algorithms. And the flavors of greedy that we talked about were the exhaustive one. I guess we talked about exhaustive before we did exact, but it's only it's only one algorithm. So for greedy, we talked about exhaustive, which is for each row, we just look at all possible rows and pick the one that covers the most. So we're greedy that we're covering as much as we can each time. Then we talked about the random method, which is what you're implementing in homework 4. Then we talked about the density algorithm, conditional expectation, which is just a deterministic version of the random one. And then last time we talked about anti-random and IPO. Although they aren't really the same algorithm, they were just grouped together because they're just 2 more greedy algorithms. So anti-random was, instead of covering as much as we can, we just find a row that is as different as possible from every other row we've ever picked for some notion of different. And the motivation behind that was we wanted to cover interactions that never have appeared before, and by picking a row that's different as possible from all the other ones, it's more likely to cover things that haven't been covered before. And then IPO was this strategy of, well, we want to, instead of just making the array with a fixed number of columns, I want to add more columns and then maybe add rows at the end. So we had these 2 parts of it, which are the horizontal extension, which is adding a column, and then the vertical extension, which is adding any necessary rows at the bottom. So you may be thinking, okay, we got a lot of greedy algorithms here, and some of them you can produce an array that's asymptotically optimal, so logarithmic and k, for random and density, and exhaustive. Oh, yeah, exhaustive I think does too. IPO is open. So I made a mistake on last Friday when I said that the ATEACH algorithm doesn't get logarithmic performance. It's really IPO that doesn't get log performance, which is a project in itself. But you may be thinking, okay, we got a lot of greedy algorithms. You're pretty much every time you're trying to cover as much as you possibly can in the first set of rows. Then you may be thinking, well, if we have a testing situation where we are constrained by the number of tests that we can perform. So I think I mentioned this a while back, but there is some work in the Navy where each individual test takes $40,000 to run and 12 hours. So it's obviously a good idea to minimize the number of rows, but if maybe we want to sacrifice coverage. So if the number of rows that are given by a covering array is too much, then we may have to sacrifice some rows. And then the obvious thing to do is let's try to cover as much as we possibly can in a limited budget. So if we have, let's just say 100 tests that we can run in some array, and then maybe the covering array number, the minimum number of rows, is for whatever the parameters are, let's just say is 200 for whatever reason, 200. So the obvious question is, if we're limited to 100 tests because of cost or runtime or man hours or whatever, some kind of cost is limiting us, which test should we pick for the 100? So we could just randomly sample from the 200 that the covering array gives, just pick 100 at random, and that will give us some amount of coverage, but we obviously want to maximize the coverage. So in the smaller array, we may want to maximize the coverage as much as possible. Okay. So this is obviously an engineering optimization problem. We have some constraints, some cost, whatever, and we have some objective, which is having high coverage, and there's competing objectives. So if I want high coverage, I'm gonna have to have a higher cost, and if I want lower cost, I must have at least smaller coverage. So it's just how do you actually determine which rows to pick? Well, what do the greedy algorithms do? The greedy algorithms say we're making the rows one at a time, I guess, except for, no, exhaustive too. Every single one of the algorithms we talked about is making one row at a time. And what it's doing is it's picking the best, or at least the average, every single time. So exhaustive said, just pick the absolute best row you possibly can every time. And the random and density method, well, we don't guarantee to get the optimum, but let's just get at least the average. And anti-random and IPO don't really have that same objective, but it's still one row at a time, trying to cover as much as possible. But that's not like what the algorithms actually are searching for. They are just, that's the goal of the algorithm. So the greedy methods are actually trying to cover as much as possible in the early rows. So if we want to say have 100 tests, well, let's just run the greedy algorithm or whatever algorithm we want for 100 tests and then just see what happens, because it obviously is covering as much as possible every single time. So if we just run the greedy algorithms, whichever one you want, for 100 tests and then just stop it, then we get really high coverage because we're covering a lot in the first few rows. So that's an idea. So to get early coverage, so early coverage means covering a lot in the first few rows. So so this is just an idea. It may not be the best, but it's just an idea. Run any greedy algorithm until the max number of rows allowed is reached. And if you happen to get under the maximum number and you finish the array, well, great, you're done. So you don't have to do any more. It's just, it very often is the case that the best known covering array is too big. So that's one idea. So, and yeah, but some people think, well, the greedy algorithms are too complicated. So, I mean, look at the code that I had to implement to actually do this. I'm not saying that I'm a great coder or anything, but I'm just saying to implement the density algorithm takes a lot of knowledge about how the algorithm works, and there's a lot of pitfalls that you can actually get into. So like if you are using a float versus a double, there were some instances where it actually did make a difference, whether you used a float or a double here. So it's not like they're really interchangeable here. So you have to be really conscious of how to actually implement this correctly. So greedy algorithms are, some people just think are too complicated. And most commercially available tools that exist out in the wild either implement the ATEAGE algorithm or the random algorithm, not any other greedy algorithm. So what people think, well, let's just try making the rows uniformly at random, because we showed before that they get logarithmic performance, which is good. And if you just run the row, if you just add rows uniformly at random until you get at least the expectation, well, that is still covering quite a bit, is covering at least the average. Yeah, so most testers don't run the whole set of tests because they're constrained by cost or something else. Yeah, so testers want early coverage, which is covering as many interactions as possible early on. Yeah, so you may think, well, the greedy algorithms are actually doing this. So they are producing as much coverage early on as possible. And if we want early coverage, isn't that exactly the same thing, right? So greedy algorithms cover a lot in the few rows at the beginning, and testers want early coverage, so they should implement greedy algorithms, right? It seems reasonable, right? I mean, that's what I thought until I looked into this. I mean, I didn't produce these results, but I looked into this. So it turns out that these are different objectives. And this would also be a nice project, is when does early coverage, when is early coverage different than the greedy algorithms and what they produce? So this is not something that you really need to look into for all the details here. What this will just show you is that they are different objectives, and it's just not really the same thing. So when you want to actually look at early coverage, which a lot of testers do, you'll have to use some other techniques in general, because we can show that you can get better early coverage when you use some other algorithm than a greedy one. So let's look at a particular, so this is a case study. So we're looking at strength 4, 7 columns, and 5 values. And if we look at a random approach versus a greedy approach, we would want to say if these are different objectives, one gets better early coverage than the greedy one. The random does better than the greedy in terms of early coverage. So it turns out that greedy, the best with say the density algorithm, produces a little over 1,200 rows. And you don't have to look into this. This is just here for completeness. It just shows you that there is a simple formula, a formula where you can just plug in values and out pops a covering array with substantially fewer rows. So this method is called a combinatorial construction. And we will talk about this after spring break. We'll talk about some combinatorial methods. But the combinatorial methods basically just mean you plug in each of the values in each of the rows and out pops a covering array, no computation needed. So with random, you had to calculate how many interactions are being covered in the row you're adding, whereas here you don't have to do any computation. So the combinatorial method obviously gets fewer rows than the 1200 row one. Yeah. So let's look at what actually happens. So if you actually do a plot here, what it actually is indicating is we're going to look at each of the tests in order and see how many uncovered interactions are left. So if we have an array, say here, then after the first test, we're going to make an indication of how many uncovered after this row. So we make the first row, figure out how many are left uncovered. Then we look at the next row, see how many left are uncovered. Third row, how many left are uncovered. And then we keep going until we don't have any left uncovered. And this is what is the result. So the solid red line, so that is the density algorithm. The blue one is, well, let's see, yeah. So the blue one is the 1100 row guy. The purple one, I'm not sure what the meaning of the line here is, but it's dotted. So the purple or pink random one is when we're just making rows uniformly at random. And the green one, which is even less than 1,000, which we're not going to look at, is just another combinatorial method. So one thing that you should notice here, so among the early tests, which one is the best for terms of how much we're actually covering? Yeah, density. And how do you know? Because the red line's the bottom one. So it's covering a lot at the beginning, but it suffers at the end here. So it has only a few interactions relatively at the end, but it requires even more rows, which is kind of sad. And even the random one, that's even worse. So when it has only a few tests, it goes off the end of the figure. So yeah, so that's actually one of the really big issues with these greedy methods, and it's a great project idea too. So if we instead of just running the greedy algorithm until completion, let's stop it beforehand, like say with a few rows that would be left, and use some, say, an exact algorithm on the remaining interactions. So like say for the red plot, maybe we stop it like right here. So after 600 or whatever tests, we stop it right there, stop the algorithm, and then use some other algorithm. And maybe that'll cause the plot to go down like that. That might be entirely possible. And there is some evidence based off of work that I have just done that that is the case. That using different algorithms in what are called stages allows you to stop an algorithm early and allow you to get a substantial improvement by using a slower algorithm at a certain point. So stopping it at a certain point using a different algorithm is often a really good choice. But these are just run to completion. So the thing that you should notice here is right down here. So what do you notice about the blue and the red line? Which one hits zero first? Yeah, the blue one. But notice that the blue one had worse early coverage than the red one. And this is something that I've actually experienced as well in some of the work that I've done, where you have really good early coverage, but you suffer at the end because of the choices that you made in earlier rows. So that's just something to notice here, that even if you have worse early coverage, then you can still get a better result than if you just use these algorithms directly. But what if we use a combination of both? That might be something to look into. Okay. But it turns out, well, this is for a, yeah, go ahead.
Well, if it's like if you suffer at the end because of the choices you made, then how is switching over gonna help if you're lacking tests?
Exactly. So that's actually one of the questions that I have on homework 4. So the short answer is no one knows. This is an ongoing research question and why it would be a great project idea. But what I suspect to be the case, and I've seen several examples of this, so I think it's true, is at the very end, you have some interaction, a bunch of interactions that are what are called incompatible with each other. So they can't appear in the same row. So that's why I have the question 3 down here, because I suspect for the last few rows that you have a very small number of interactions left, but the graph, if you make the incompatibility graph, has high chromatic number, meaning that you need a lot of colors, i.e. a lot of rows at the very end, because they're all fundamentally incompatible with each other. So that's why I suspect that to be the case. I'm not sure why that arises, because the density algorithm isn't like making a specific choice as to which columns and values to pick, because there's a lot of tie breaking there. So maybe a different tie breaking strategy is better, but no one actually knows the answer to that question. But that's definitely something to look into, because obviously this type of situation down here is not ideal, where it's like, oh, we're doing better, we're doing better, we're doing better, oh, now we're doing worse. So yeah, that would be worth looking into. Any other questions about that? Okay, so I want to mention something here, which is that this is for a particular ordering on the rows. So if I order the rows like this, then I can calculate the number uncovered after each row. But what if I reordered the rows in a different order? Well, I still have a covering array, but I don't necessarily have the same number of uncovered interactions each time. So this plot right here is for a particular ordering. So it's not like, say that this is true no matter how you order the rows. It might be better that ordering the rows in a different way is a good idea. And that's a project in and of itself. If I have a covering array and I reorder the rows, what is the best ordering? If I produce an array from the density algorithm, for example, will it be the case that if I just switch 2 rows, I will always get a worse plot compared to the original, because density covers the most it can each time? So that might be true, I'm not sure. But it turns out, well, just because it works for one ordering of the rows doesn't mean that it necessarily will occur for every ordering of the rows. So it turns out that in this particular case, it works for every order of the rows. So is there any way that we could reorder the smaller array to get better early coverage than the bigger one? So the bigger one has good early coverage, the smaller array doesn't, but it might be there might be a way to reorder the rows of the smaller one to get better early coverage than the bigger one. It turns out that this is not possible. And I'm not going to go through all the details because it's pretty heavy on the math, but the basic idea is we're going to calculate what are called private interactions. So private interactions are ones that only appear in one row and in no other row. So if, say, we have 2 columns here and we have a 0, 2 right here, and nowhere else the 0, 2 appears. So in this row right here, this interaction's private. So it only appears in that particular row. And if a covering array is minimal, meaning I can't remove a row, then that means that every row has some private interaction. Because if a row has no private interaction in it, then we can delete it. So we just assume that every row has a private interaction. And what you can do is analyze the two arrays that are generated and calculate for some ordering, how many interactions at most are covered and are the result of being a private interaction. And it turns out that you can actually show via some analysis, and I'm not going to go into it, that no matter how you reorder the rows, you will not get better early coverage than the bigger one. So they aren't actually the same question of early coverage versus small size. That's just something to keep in mind. And this is the last slide for this set of notes. Yeah, so the smaller array does not have as good early coverage. So few rows does not imply good early coverage. And if you have early coverage, of course, that doesn't imply few rows either. So yeah, one question that some people have been looking into in a theoretical context, but not in a practical context, is if I limit you to, say, 100 rows, what is the best possible coverage I could ever get? So among all possible choices of 100 rows, what is the best possible coverage I can get? I might not be able to get 100% coverage, but can I get 98% coverage or whatever? So some people have looked at that in a theoretical context, not a practical context. Yeah.
This is something I was thinking about mainly because you want to minimize the number of rows usually covered, right?
Mhm.
Still have complete coverage.
Mhm.
Typically, like interactions, like, as you talked about, are across or within rows. But can interactions ever be, within can they be like vertically adjacent to each other? Like within
Oh, good point. So that is something that some practitioners have actually looked into, which is what are called constraints on covering arrays, and we're not going to talk about that much. But what you can have is, say, I don't want this interaction to appear. I don't want these components to interact together. Or I don't want this this interaction to appear after this other interaction. So that has been looked into. So maybe I don't want 0, 1, 1 to appear after 0, 1, 0.
Oh no, I literally meant like an interaction within a column.
Well, the interactions that we've defined are for rows, yeah. Yeah, I'm not sure what an interaction would be with respect to a column.
So a column, because a column obviously would have multiple different interactions.
So I'm not sure what you're trying to say. So if we have, say, an array right here.
Yeah, or if you just look at the one next to the terminal. For example,
Okay, yeah.
you have interactions like 0, 1, 0, 0, 1, 1, etc. at different row locations within that column.
So like the 0 here, the 1 here, the 0 here. So
Yes, stuff like that.
So, well, what do you want to appear in the column though?
I guess my question is, would it be the case that, let's say, you don't have certain interactions within rows, but
Mhm.
they exist in the column?
Yeah.
Is
So
that helpful at all or no?
yeah. So the thing is that interactions are between different components, and we're interpreting a row as a single test.
Okay.
So it's just that there would have, if you want to have something to appear or not appear in a column, that means that is for one particular component across multiple tests. Maybe there is some interpretation of what that would mean. Maybe you don't want, say, this type of behavior where this is 0, this is 1, this is 0, this is 1. Yeah, so that is something that could be looked into. So maybe the constraint would be the first column can't have a 1 then a 0 after it in appearing. It can only be zeros and then 1s. Well, because every interaction has to appear in a normal covering array, so every possible value has to appear in every column in order for that to work. So it's not like you can restrict a value from ever appearing, but maybe you can restrict it to say the 0 appears only 3 times at most. So that might be something to look into too. And that has a relation to coverage in terms of how much good coverage can you get within a certain number of rows. So that might be something to look into. And another one that has been looked into is this one, which is let's actually read it. So let's calculate for a particular interaction the first time that it appears. So like say for these 2 rows up here, if 0, 1, 0 never appears before this row, then 0, 1, 0 we'll just figure out which row that this one actually is. And what we can talk about is what is called the average first time that an interaction appears. So figure out where the interactions appear first, and then just figure out what the average is. Then what you can do is, let's actually figure out what that means. So that says the first time that this interaction appears, and we want to find the average. Well, if a fault exists in a system, and it's a result of this interaction right here, then let's just say that chi of t is the 10th row, for example. And suppose that t is the faulty interaction or a faulty interaction. Well, in the 10th test, we will find a fault occurred because t is in this row for the first time. So what this is interpreting is the average number of tests before we find a fault, before we can detect a fault existing. So if we look at the average, then that is what is called the mean time to failure. So this is called the mean time to failure. And if we try to have early coverage, then that means that a lot of interactions are at the top, meaning that the mean time to failure is earlier. Yeah. Oh, I thought you had a question. Yeah. Oh, sorry. Yeah, sorry. Thank you. Yeah, so that's the mean time to failure. And we would want the mean time to failure to be as small as possible so that we can run fewer tests on average until we detect a fault. So that's what practitioners want to do. They don't want to have to run all tests if there's a fault in the system. They want to run tests until they find a fault and then they stop. So when there's something wrong that occurred, they just run until that occurs and then they go and diagnose what the problem is. So the mean time to failure is how many tests on average do you have to run until you detect a fault? And you would want that to be as small as possible. So is there a relation to early coverage? And my intuition is no, because if you have early coverage, then there's a few interactions way down later that are skewing the average down. So if it's more spread uniformly, then there isn't such a skewing of where the mean actually is. But that might be worth looking into as well for a project. Okay, any questions about early coverage? Okay, I'll see you on Friday. Are the presenters ready to go on Friday? Or are they not here? Yeah, so you may want to talk to each other. So, cool. I'll see you Friday.